Welcome to qnawire.
In this case, we have solid wood door in a gymnasium that's open, and a basketball hits it. It's pivoted about its one side here, and the basketball hits it. And we're told that the basketball exerts a force of 1,500 newtons over 8 milliseconds on the door. So, but what we have here is an impulse, and we'll have an angular impulse if we because again there'll be a torque. So how we work this? Well, let's see here. The mass of the door is 35 kilograms. Its width is 1 meter. Its height is 2 meters. That doesn't actually matter in this problem. And the ball hits the door right at the center. So the mass moment for this door is 1/3 m1 w squared. Okay, so that's a w, not an omega. Make that look a little better. Omega w squared. Now we have our moment balance says that the rate of change of the angular momentum about the z-axis, which is out of the page here, is equal to the sum of all the torques about the z-axis. Well, we can integrate that from one time to another, to a new time. So that tells us that the integral from t1 to t2 of tau z, and again, I got rid of the summation here because we basically just for notational purposes. This is the sum of all the taus, so dt. So that is like our angular impulse, and that equals the change in integrating this gives us the angular momentum at state 2 minus the angular momentum at state 1. Now, if tau z is roughly, if these two times are very close to one another, so this is very short, and we can say that tau z might be pretty constant in a short period of time. It's roughly constant. So we can say, well, this would give us an average. This kind of a mean value theorem would give us some average tau z times delta t. Okay, so doing this integral basically is same, assuming that this is a constant. And well, we know the angular momentum of the door initially is 0, so that goes away. And so in the final state, it is just j times whatever its angular velocity is. That's what we're looking for. And now the torque over this delta time is just the force that's acting over that time times w over 2, because it hits halfway along the door. And then we have delta t. So omega equals f, the force, times the width of the door, times the time over which the ball was in contact with the door, divided by 2 divided by the mass moment. So now we have, we can see substituting in the mass moment, we get w cancels out, one of them. And so we get 3 halves f delta t all over m1 w. And plugging in our values for that, we get 0.514 radians per second is the speed of the door after the collision.